Okay, hopefully it's recording. Great. Let's talk about making things move in FRC. So I know that you guys have all seen parts of FRC before. I think this is supposed to be especially helpful to the kids that have maybe seen the robot things, but are used to like the FTC rules and the FTC motors and such. And so this is really just a focus on, it's not there's some numbers, it's not really in depth, it's mostly meant to focus on what the rules say your options are, which parts of that people actually use practically, and why you would use it in each place. Okay, cool. So we were talking about this a little bit while we were sitting here before, and as you mentioned, right now in FRC, there's no strict limit cap on the number of motors you can use. However, there is a really specific table in the rules that says these are the types of motors you're allowed to use. So of course there's many types of electric motors in the world. I guess thinking about this in FRC is pretty simple because you have to pick something from this table. And so you'll see the stuff that you're used to, like actually sim motors come with a bunch of different part numbers, but they're basically all the same. You guys are probably familiar with the RS775 Pro. There's this category of motors called vane bots that maybe, if you're looking at modern FRC, you might not see this much anymore. But this is like the older, like the regular RC motor. Like if you're doing RC cars, you'll see 550 and 775 style motors. They're like, it describes the size of the actual motor can. And then there's all these, and a bag, mini sim motors, but then there's all these other things down here that you might not really see very much. So do you guys know what a window motor is? Okay, besides the mentors. See, okay, so what that tells you is that basically everything down here at the bottom half of the table is like historical FRC.
Well,
Except for the brushless.
well, yeah.
Minus the, ignore the brushless.
Before you used to be limited to like how many sims you could use.
Yeah, it'd be like 4 when I was in freshman.
Yeah,
Right.
And then I was 6. Oh my goodness.
I know,
Six.
right? Wow, 6 motors.
It was amazing. So like the window motors were like the motors that you could use. That were like, yeah.
Oh, I should have put a picture of a window motor in, but the window motor was basically a smaller, like maybe a 300 or 400 size motor. So it's like half the size of the 775. But the nice part is, remember that this is also before versaplanetary gearbox existed. So the window motor was already connected to a worm-style gearbox that turned the output 90 degrees and already had like 100-to-1 ratio. So so this it was very useful as we go through the later parts. Okay. So, but this also brings us to the idea of motor limits. So like you said earlier, I think there's, so this year they finally got rid of this. There used to be an extra column on this table in the rules that said how many motors you're allowed to use. And this year they just dropped it from the rules entirely. But I thought it's been like this for longer than it has, so I went to look it up. And actually there was a motor limit for how many sim motors you could use as late as 2017. But it kind of seems like it's not going to come back, so let's cross your fingers and see what happens. In practice, what it means is that you can have as many motors as the number of places that you have to plug it in. And unlike in FTC, where you can put down another rev hub to get more motors, you cannot put another PDP on your robot. So 16 motors, take it or leave it. It's a lot for pretty much every situation, but you do still see some stuff like this year Madtown ran out of motors, partially because they do swerve drive and that takes 8 minimum. And so they had to do a power takeoff for 2 of their mechanisms to get what they wanted. So you can still run into it. Okay, cool. So next, let's talk about why. So there's this huge table of motors. Most of them, like at least half of them, you've probably never seen in a competition if you went in the last 2 years. Let's talk about why that is. Basically, FRC motor, the stuff that was in an FRC competition used to be largely surplus parts. So they would get like old parts from, like extra parts from the auto industry or something, so it would change from year to year. But FRC got bigger. What's that?
You got auto parts, we didn't get auto parts.
Well, I mean, you kind of did the window motors, for example,
true.
where they would randomly ship you left and right window motors because they didn't know what was going to be extra coming off the assembly line from Detroit. Yeah. And it's like the snowblower motors only showed up for 1 year because I guess they only like messed up making snowblowers 1 year. Anyways, okay. So what's happened in general is that the first suppliers have made specific motors for the competition. And so what you ended up with, so like Sim was, I mean, it's like a mass market motor, but first basically contracted to have somebody make it, and it's just been around forever. And then Vex made the variant that's mini Sim, Rev made the Neo motor, and what's really striking about all of these is that they're all in kind of a sweet spot for how fast they need to turn to be in an FRC drivetrain. And relative, so I probably should have put like a old 775 or like an old 500 type motor on here. But see, both the Neos and the 775 pack way more max power than you would see in like a normal like RC car motor.
They're higher quality motors. Like the
Yes.
old Banebots were.
Yeah, they would like burn apart.
Yeah.
You would like look at them wrong and there would be smoke coming out the back.
I remember that.
Yeah. So anyways, the general theme of this table is that the motors that aren't on this table, so okay, from the other conversations about motor curves, we talked a lot about what the free speed of the motor is and what the stall torque is, and these kind of both go into what ends up being the max power in of the motor. So it's basically like you put so much electrical energy in, and yeah, like,
Pop quiz. Where's the max power?
oh boy.
At what percent stall torque?
It's a good question. Do you remember what the graph looks like?
Max power is at what percent stall torque?
Oh, there's no space.
Basically 50 because
Is it the?
Yeah.
Okay.
That's right.
So
Yeah. When you look at the motor curve, it was like the red, or at least on the Vex website, it's the red curve, red parabola in the middle. I think it was red. Anyways, the theme of the things that aren't on this table is that they either spin too fast or they don't have a max power that's even close to these. So people just don't use them because they're just too weak for most mechanisms that you want. So since you're only allowed to have so many motors, people basically choose one of these. So then you get towards how do you pick one of these options for your mechanism. So in the last presentation that Ian gave, we talked about, we spent a bunch of time calculating like, well, you need this much torque to come out of the motor, and so which means you need to run it like at this speed, and then here's the gear ratio you need, right? So I think this one was explicitly in the presentation about shooters usually like to be 3 to 6K RPM. So just to, to fill in some extra parts. These are all really rough because it depends exactly what you're designed for. But elevators, it kind of, like shooters are probably one of the faster things to do. So sometimes people don't even run gearboxes with them. Because if you can see that 3 to 6K RPM is actually about the free speed of like the sim style class motors, right? But then as you go down, elevators are still fast because the spools are small, but they're not quite as fast. So you might have a little bit of a gearbox. 4K RPM for an elevator is probably really fast. But let's call it maybe 500 to 1,000 RPM, right? So you can start to see how this impacts how many gearbox stages you need when you compare the different types of motors, right? Drivetrains go even slower, so maybe like 200 RPM, and then arms are even slower than that. Like 100 RPM means that your arm's completing more than a full circle a second, right? So let's call it maybe even lower than that, maybe 20 RPM or less, right? So all of these numbers, except for shooters, are way lower than all of the free speeds in the table here. So then the logical question that might come out of that is, when you go and look at the best teams robots for basically until this year, a lot of people would talk about making everything out of 775 Pros, right? They would talk about like, we built an elevator and it has 4 775s. We built a drivetrain out of 6 775s, right? And so you'd be like, well, why would you do that when you have to add an extra 4 to 1 stage over here just to drop RPMs, right? Like, so the 775 and the bag are basically, they spin an order of magnitude faster than the bigger, slower motors like the Sims. Basically all comes down to the FRC weight limit. So the Sims are nice because they spin a little bit slower. They still have like a pretty high max power cap. I mean like 400 watts is kind of a lot to sink into a motor. We don't usually actually use them at 400 watts, but that's like just to keep apples to apples to compare them. Because this would probably, if you were putting 400 watts into it, you'd probably be pretty sure you're blowing the 40 amp breaker. But that aside, the difference is that these motors are like super solid. So like if you hold a Sim, you're like, it's not just a paperweight, it's like you're holding like a vice or something, right? And so when you divide how much power you can put into, how much power the motor can sink by how heavy it is, you get the power density. And basically the 775 wins all the battles of power density. So if you were designing your own custom gearboxes, a lot of times, and you really wanted to optimize for the least weight, you would pick things that are over here in the, like, I mean, look at this, like 400 watts per pound versus 120, 100 watts per pound. Like, it's a pretty obvious choice. Except this year we got a new motor in the mix, which is the Rev Neo motor. And this one, thanks to it being brushless, it's way more efficient, so they don't need as much weight to sink the heat into. But they made it so that it's the same shaft size and roughly the same free speed as the Sim motors. And so now you have this thing that's like basically power density equivalent to the 775, but in many cases easier to integrate. So we'll see exactly what happens to that. I mean, we're already starting to see people trying to like building elevators out of Neos. 254 did the drivetrain out of Neos at the last minute last year. Yeah, we changed our drivetrain at the last minute. It's for this power density ratio. So we'll see where this goes. But
yeah, but I mean, the thing is, this team has replaced a Neo. We replaced a bunch of 775 Pros, but I don't know if we've ever replaced a Sim during build season.
yeah, that's fair.
So
That's
there's,
fair.
There's yeah.
Okay, yeah, I mean, and I think that is reflected in that. What you take by in both of those situations, where we use a Neo instead of a 775, or we use Neo instead of a Sim, or use, whatever, any of those cases, it's because you're trying to push more power density, and you get that by cutting the weight. The weight is there because it gives you a lot of extra margin. Yeah, anyways, do you have any questions about the motors and stuff? Or at least the specific motor selection and the numbers. Okay. Yeah, so hopefully, Vex has a pretty good, so actually down here, motors.vex.com, they have a pretty good table laying out most of this. They don't have the power density, so I added that part. I just calculated it quickly. And they also don't have the Rev motor because they don't have the Neo motor because they're not Rev, they don't make that. So hopefully having this all in one place kind of makes it easy to look at. Cool. Okay, so let's talk about how you take your motor. Let's say you decided based on that table that it makes a lot of sense to put like Neos on your elevator, for instance, right? So then it's like, okay, well, how do you bridge the gap between the Neo wants to spin at like almost 6K RPM, and if you put your elevator at 6K RPM, it would probably like fly off the top. So we need gearboxes. So there's a couple different ways this could come. I tried to put a lot in this one slide, so it's very cluttered. So if you're looking for examples of how to make slides, probably not this one. But there's a bunch of different, okay, so there's also a section down here where we'll talk about custom gearboxes. But before we get to that, one of the great parts about FRC now is that there's lots of off-the-shelf parts. because there's been this whole thing between, you know, big heavy sim motors and like smaller, like 775 like motors, the gearboxes have also fallen into those two categories up to now. So at the drive side, you see, like we've been using these Vex ball shifters for a long time. They let you put things like 1, 2, 3 motors in. You can get shifting versions, you can get non-shifting versions. Yeah, those are pretty nice. One thing that separates these two classes is that these bigger motors have a larger diameter shaft that doesn't really work the same way with these smaller ones. So there's a lot of options in these that you can take. You can change like sim motors, you can use mini sims. Now you can use Neo motors. They all have the same little output shaft. They all have the same bolt pattern on the outside, so all the parts work together. Then there's, wait, do you have a question?
No.
Oh, yeah, so then there's this other category of like, okay, so you take the smaller motors like the Vex in the bag. They're basically like a third of the size of one of these, so you can't just plug it into the gearbox. It the holes don't line up. And there used to be different ways that you would do this, but since the Versaplanetary came out, basically everything revolves around the Versaplanetary. Because it's just such an effective solution to this problem. So you see it all over the place. For instance, like these are two pictures from different years of Citra Circuits, 1678 robots. You know, this is their crawler to move themselves forward onto the HAB platform. It's, you know, I mean, just like what we had in our robot in 2019, it's a 775 stuck to a Versaplanetary with like
We did a bag.
2 stages.
We did a bag. but
Oh, we
it's
use a
very
bag
similar.
motor. Okay, fair. It's pretty similar. Actually, maybe this is a bag. No, I think that's
No,
a
I
775.
assume
It's got a little thing on the back. Anyways, Versaplanetary makes this really simple to not think too hard about this, and even teams that will like this picture down here is a picture of the custom elevator gearbox from 1678. Just because they know how to make these gearboxes that are super powerful, have shifting, whatever in them, on a lot of places for manipulators, they just don't want to think about it too hard to use one of these, use a Versaplanetary. Now, in this range, you also get some options like there's the doubler, which we've used before, so you can put 2 motors into one input shaft on the Versaplanetary. You could put like, I don't think that there's any off-the-shelf shifting options for 775s. So that's one of the things you kind of lose in this category.
You technically could, there's like a sim adapter where it does the reduction so that the 775 spins at a similar speed to a sim. And then you can plug that into a shifting gear.
Oh, I thought that went the other way.
The sim to 775.
Yeah, I thought it went sim to Versaplanetary. So I know there's a sim
Oh yeah.
to Versaplanetary
Yeah, there is
adapter.
one of those too. But Andy Mark sells a like an adapter for a 775 or
So you can, okay, so
for a Fisher Price motor, but yeah.
for Fisher Price motor. Speaking of motors that are historical, literally came out of children's toys. Right. Okay. So I guess there probably is an adapter where you can go from 775 to like a super shifter or a ball shifter or whatever. But typically, if you get into the case where you want to take a 775 and put it into an environment where you want shifting or you want more than 2 motors, it very quickly gets into the realm of teams that design custom gearboxes. And so there's a couple of reasons why you might want to do this. So I highlighted a few down here. So one of those might be, I just want like a massive amount of power. And so like, there are actually a couple of elevators the last 2 years where you can see that there's 4 775s clustered around like an input gear. I think this one also has shifting in the same gearbox.
Yeah.
It's super compact. It's crazy amount of power that's sitting right there. But it's also like quite a project to build something like that. So these are both elevator gearboxes down here. This picture doesn't come out that great, but I'll post some of mine. So the other big reason to do this is if you need the motor to fit somewhere, and it's really hard to fit a Versaplanetary gearbox. So for instance, there were a couple places like this is from 2018 Citrus Circuits class, 1678 Citrus Circuits.
Designed originally by 1323.
Yeah, I think this might have been.
Yeah.
Oh, was this the same as their? Okay. 1323 doesn't post as many pictures, so it's hard to get stuff from them. But they designed the 775 right into the side panels of the claw, and then it's a roller claw with a bunch of wheels coming out the side. This packaging is it's also really similar to like what Aaron was working on the new combo intake for off-season stuff, where you stick the motor between the two parts. In that case, it's kind of a toss-up on whether it makes sense to just stick a versaplanetary stack in there too, but if you're already gonna design plates for the side and you don't need that much reduction, it sometimes makes sense to just drop the gears in. Cool. And then there's like these crazy examples, like where 254 was like, well, we're gonna make the elevator really narrow, so the only way we could possibly put two gearboxes in was to design them interlaced so that the motors are at the bottom and then you have shafts all the way up with gears next to each other, which is this picture in the middle. Which is a little bit of an extreme example of how to do packaging, but shows you what's possible. All right, cool. Any questions about the general gearbox options that comes with these motors? Cool. Okay, let's talk about controlling them. Okay, so like we were talking about earlier, all of these things have to be plugged into the PDP. The PDP only has 16 channels. So I talked a little bit about how the rules say that you have to have one PDP channel to one controller to one motor, which isn't entirely true because there are actually a couple motors in this list down here. So so I think this was actually from the wrong year rule, but in 2018 it was R36. These rules basically don't change. They might change number, but they're basically always the same. Automotive window motors, maybe Fisher for snowblower motors.
Fisher Price doesn't exist anymore.
Yeah, something like this. These all have 2 motors per controller, but the thing that you might notice about these is that none of them are circled because none of them make the common motors list.
You have to be doing some weird stuff to be like, oh, we need the extra motor for this, and we don't mind that it's a lower power motor. Like, it's super weird for us to ever do that.
For sure. So that's why I say the simplified version of reading this set of rules, which is really like 5 or 6 rules in the manual combined, is that it's one channel, one motor controller, one motor. So also a difference from FTC is most of these motors are much more powerful. So rather than having the controller actually built into the rev hub, the motor controller, the part that converts the program into the actual power that goes into the motor, is basically this extra module. It's like maybe about the size of like half of a fist, and you got to wire them all up individually. So the 2 most common, so they're pictured here. I mean, I know you guys probably already know this, but the 2 most common ones are the Talon SRX, which is all the DC motors, which is basically everything in the table except for the Neo brushless motors, which came with their own controller, because when they say brushless, what they actually mean is an AC motor. So it actually has no switches inside. You have to have a really fancy controller to make sure the electronic signal is going at exactly the right time. And so that's why the Spark Max that came with that Rev also made to go with the Neo motors comes with these 3 wires on the output. So they're basically the same size. They have almost the same connections. We just have to make sure we wire the correct one up. Cool. Motor controller questions? Okay, let's talk about something super different. So I think you guys have probably seen a lot of the motor stuff. So you're familiar with that. However, what's usually a little bit more hidden in the robot and kind of does magical things is the pneumatic system. So there's there's actually a lot of flexibility in the rules as to what pneumatic outputs you can use. So there's like cylinders of all different sizes. You can get anything from like a little 1/2-inch like stubby movement. So for example, we might use those in the gearbox when all you need to do is like shift between one spot to another. The rules even allow you to use like rotary pneumatic motors. It's kind of fair game there. The part where they get you is that you can only have so much air in the system, and you can only switch so much air at one time. So the rules are really strict about things like the compressor, the system pressure, even down to like the exact size, or the maximum size of the fittings on the solenoids. So the solenoids are the part that, kind of like a motor controller, they let you flip air from one side to the other.
Even max tubing size. I didn't even realize they had that rule. They have solenoid max valve size and max tube size is 1/4 inch.
So I couldn't actually find the max tube size
I just read it
rule
like a
later.
day ago. It's there.
Okay, I remember it being there, and I remember it
I
being
thought
a
it went
reason why I
away, but
couldn't buy some
apparently it
parts.
didn't.
But I couldn't actually find the rule, but I'm sure it's there somewhere. There's an explicit rule that says your solenoid can't have more than a 1/4 inch tube or 1/8 inch hard connection. And that one's been there forever. Yeah, anyways. So the reason this matters is because,
I was just gonna say, I will admit to having failed people in inspection because they have the wrong PSI in
Oh,
their
yeah.
system, and like, that can hurt you for like a day, cause it's hard to, like, I've seen it like derail teams, everything's fine, and then they can't fix their pneumatic system. I feel
Yeah.
bad.
well, if you design for a higher working pressure, or if you, not even design, if you
Working is
tested
stored.
it
Okay.
at a higher working pressure, you could be in trouble.
Oh, that'd be bad. That inspector. Ooh. You're
Yeah.
saying because it's structurally.
Well, like, what if it only works if you're, okay, so the rule, so I did write it down in here just for the record, is, the rule is 60 PSI working pressure and a 1/4 inch tubing. So when you're calculating how much force you can get all these pistons and how fast they fill up, these are basically the things that matter. But yeah, like if you designed, like when we had the unfolding elevator, like, what if we accidentally tested it at 80 PSI and it like barely worked, right? And then we got to inspection and we had to change it to 60 PSI, we would have been stuck in a hard place. Okay.
And like, the reason I'm bringing this up is this is like really important to make sure that you're aware of like from day one.
Yeah.
It's really hard to fix on like
Yes.
inspection day.
Yes.
I've seen it completely kill teams.
Yep. Okay, so there's a bunch of different kinds of cylinders. I don't actually have the smallest one, but this one is probably like the regular 3/4 inch bore. So that means that there's a circular plate inside that has a diameter of 3/4 of an inch. So if you take the pressure and you calculate the area of the piston inside, you can get how much force pressure there is to come out.
Pressure is just force divided by area, right?
Oh yeah, maybe I should have mentioned.
If you have like a pin, right? Even though you don't, or a needle, even though you don't push much force behind it, you have a lot of pressure, so it can go through things, right? Because the area at the tip is really small. If
Yeah.
you have a larger area, right?
And pressure
So-
is conveniently called PSI in the metric system, which
Right.
is pounds
No,
per square
Wait,
inch.
not metric,
Not
but
metric.
Or the non-metric system, the American system.
yeah, so what does that stand for again?
Pounds per square inch.
Right, pounds per square inch, so that basically tells you exactly the formula.
Yeah. It's convenient.
Pounds divided by area in square inches, there you go. Right, but because you have a fixed amount of pressure and a fixed amount of like airflow based on the size, right, so you have a fixed amount of air movement that can happen. A lot of times the most effective pneumatic systems actually use smaller cylinders, and so that's why it's harder to see them from the stand, so you know that stuff is moving, but you don't exactly know how it's happening. So a lot of times, like this is actually, I would classify this not even as a small cylinder, it's kind of regular sized, but like, if it was buried in the robot and you were far away, you probably wouldn't even see that it's there. Part of the reason to use these mini cylinders, so this is maybe like a regular 3/4 inch bore, but okay, so this is 1 inch of stroke, right? It moves like this, but look at how much metal there is just to get this much movement, right? I mean, admittedly, if you needed to create this motor with create this 1 inch of movement with the motor, it would probably take a lot more metal and you need more gearboxes and whatever. But if you wanna be even more efficient with how much metal there is behind it, you can get these like, so the 9/16 bore isn't even that small, but it does cut the weight of the cylinder about in half for the 1 inch of movement. It also makes the cylinder a little bit shorter because the end caps aren't as big. And then they make like, there was actually, I think I saw like maybe like a 1/4 inch bore or something on a robot that was at SVR this year. That's probably a little bit smaller than is worth it because there's not that much like force that comes out of it. Cool. So you can also get really big things like this is like a 12-inch cylinder, and at this rate, 3/4 inch makes it look really skinny because like the amount of metal, the end caps are basically the same on all these cylinders, and it's just the part in the middle that they change. So this makes it look like a really good value. And then you get things like these cylinders, which I think were maybe 1.25" bore.
I think it's 1 inch and 16. I think we
1
compromised.
16.
Yeah, I'm pretty sure it's 1 inch and
Yeah, we
16.
probably should have made them bigger, but anyways. So these lifted up the entire elevator in 2018. So they would like unhinge the whole thing. And honestly, they probably should have been even more powerful. It probably should have been bigger bore. The trade-off is that when you get a cylinder this big, you literally have to agonizingly watch it open up because only so much air flows through here, so it goes like this when it's opening. and then you've blown your air tank for like the first half of the match.
There's a trick where you use smaller diameter cylinders, but more of them. That can speed it up if that's a real issue. Because then you have multiple flow restrictions, which add up to a bigger hole, basically. You have a bunch of small holes, which is a bunch of,
Yeah. Exactly. And but you do end up using more. I mean, you're switching it through more solenoids.
Yeah, you could do more solenoids,
To
or
get
you
more
could do
flow.
the same solenoid, but I don't know how much faster that would be.
Yeah. So there is a point where there's the pneumatic control module, the PCM, kind of like the PDP, also only has so many slots. But you're allowed to use at least one more PCM, maybe even more than that. I forget exactly. Okay, the other type of cylinder that I just wanted to touch on is they make these short stubby cylinders called pancake cylinders. They barely move at all, maybe like a 1/2 inch, but it's enough to do actions like shifting a gearbox, unlatching a mechanism, maybe like holding, when I say latching, maybe something like holding something in at the beginning of the match, and then as soon as you start, you open it up and it just falls out of the robot. Say if you need to keep something inside of the frame perimeter, that's really common. Okay, cool. So pneumatic control goes through, so there used to be a bunch of parts and you had to like wire up all these relays, and then you had to wire the compressor into like a digital input or something. And the folks over across the road electronics were like, this is too complicated for most rookie teams and it's too error prone. So they made one module called the PCM that has all the electronics that you need to do it, and it's actually kind of awesome. The PCM goes along with these solenoids. Each of these solenoids, you literally put 12 or 24 volts into it, and it flips the air from one side to the other. So in programming terms, everything's binary. In mechanical, it relates to, in mechanical terms, it's purely binary motion. It's you're in state A or you're in state B. But a lot of times that's really useful. Okay, and just some examples of effective use of pneumatics from us and from other folks. So on the left we have the elevator in 2018. Instead of having a 2-stage lift, it basically folded in half. And it has this is an example of big cylinders on the side. And on the contrary, this year when we did the hatch mechanism, to save weight, it has one of these like little tiny 9/16 bore cylinders. You can see the same thing on 1678's hatch mechanism this year. So they actually have 3/4 inch bore to open up the mechanism to go outside of the frame perimeter, but then they use the little tiny, or I should say mini, 9/16 cylinders to actually grab the hatch, because you don't have to do much sideways force. On their climber, you can see one of the pancake cylinders holding it closed, and then at the end of the match, I don't think the springs or the surgical tubing is drawn in, but at the end of the match, you can flip the pancake cylinder in, and the legs just fly out of the back. So same, 254 also used the pancake cylinder here for shifting, another common use case. Yeah. The nice part about the pancake cylinder is it's really short, so like this is literally less than an inch short, whereas if you wanted the same stroke from a regular cylinder, it would be like 3 or 4 inches long. So it's mostly a weight and packaging difference, but the actual motion is the same as a regular cylinder. Cool. Any questions about pneumatics examples?
Where wouldn't you use pneumatics? Sorry.
Oh, good question. Yeah, what's up?
Have there been any teams that were successful like without using any pneumatics? Yes.
Yes.
Oh yeah, yeah. The question is, are there success stories of robots with no pneumatics? And I definitely yes.
My freshman year in high school, we made to finals on Galileo with no pneumatics.
Yeah.
Of course you did.
We lost the 254.
That's amazing.
Guess who used pneumatics there? I'm just kidding. Actually,
I don't think they did.
Yeah.
I would
Maybe
be
for shifting. Maybe
I
for
would be
that.
not that surprised if 254 went pneumatics some years. In some cases, parts of the pneumatic system actually used to be like 2 or 3 times heavier than they used to be. So I think it was probably more common in the past for teams to actually make a conscious decision not to use them. But lately, it's been really useful to do small tasks. So. But even this year, like I think a good example was this year, 54.99. I think that's right. 54.99 at CVR. They had no pneumatics in the robot, and it was a conscious choice to reduce the number of parts. So they had no shifting. Everything was motor based, but the rest of the system was rock solid. It just meant there were some things they couldn't do, like you can do shifting with servos, but it's not worth it. You know,
the shift time is like 2 or 3 seconds, and by that time you're usually close to
yeah,
destination.
exactly. It takes too long, and it might not be reliably. It might not reliably go into the next year. It did, but when you do that, it drives some things in your design, right? So it meant that they had to do like a roller or a Velcro-based way to get the hatch, and they couldn't do something like push in and latch. So, yeah.
But that's what they did. They had like a thing.
What was it? I forget.
They had like a flip.
It was the everybody style,
For
where they have a
54.99.
little tongue and it goes in the hole and then it flips up
So here's,
and then they go out.
Oh, but then they moved the elevator to get rid of it, right?
Then they flip out the tongue.
Okay. So they had to use rotary motion to do that
Yes.
instead of having
Yes.
a linear motion. I mean, in a lot of cases you can do that. It's just
yeah, I know like a couple years in, like 1 or 2 years in my high school, we didn't use pneumatics because we didn't have the bandwidth. Like it was an entire extra system to add on, and we were able to get around not having pneumatics by using a motor in your system.
Mhm.
And so you have to just take the pros and cons of it, because it does adding a compressor does add weight too.
Yeah.
Right. Like that is another thing.
I would say nowadays all the top teams consistently have pneumatics on their robots.
Oh yeah, I don't think that there's any
Because-
reason you should design it, but I'm just saying, like, the reason that you may not is because of like bandwidth or weight, or especially for less top teams. Like if you go to a competition here, I'm not sure you'd see it, but I think if you were to go back to Virginia, you would.
it's
There's some
definitely
reliability stuff that goes along with them. I mean,
it's definitely simpler than it used to be, but it still has a lot of reliability choke points. It has a lot of potential for leaks. It has a lot more small wires
Leads.
that can break than the motor controller system does. So, yeah. Cool. Any other questions? Okay, thanks guys.
I'm just